So on Friday, we uh, we noticed that. Hang on just a second. So on Friday, we were talking about the color differences for laser, and we ask you to remember the first initials of each color in the spectrum. What I'd like you to do on Wednesday is open the chat window, respond to me only, and give those letters Roy G. Biv, Roy G. Biv, in the chat window where you respond only to me as an instructor. So we're just going to check the dipstick to make sure that people have spent some quality time memorizing those color, the order of those visible colors, because when a laser in fiber optics is the frequency changes to a higher frequency level, the data is the amount of data that can be carried by that fiber is greatly increased. And you will find in the addendum and in separate, in the resources folder, there's a really cool, and it might even be in module 1, where it shows how laser or how light travels down inside a column of a material, in this case, water in a bucket. There's a hole in the bottom of the bucket, and it explains how fiber works. And that's worth seeing, right? So those are things that you want to spend time exploring and clicking on the links. And I wish we had a chance to examine every single one of them in the course, but there you have it. The things that are in the references folder, you are expected to know cold. You are expected to know all of this. And then anything that's in the resources folder is nice to know, right? So we just want to make sure we're clear about those expectations. So student learning objective E has to do with an operational tenet. It has to do with multi-home devices. And what we wanted to do was to take a moment to call that out. So when you're looking in about networking situations, particularly in home network or small office environments, but not just there, sometimes you also have, in larger settings, a multi-home device. Now, what we mean by a multi-home device is that the device is connected to the Wi-Fi, but then there's an Ethernet port, and the Ethernet cable is also connected. And there are cases where that one device can create a loop because it's connected to the Wi-Fi network, and the Wi-Fi on the back end is connected to the cable network, but then they're also connected to the Ethernet. And that can create huge problems. And but we wanted to call out specific cases where that's bad, but there are other cases where it's a sensible thing to do, right? So you can have a multi-homed device where you're receiving cellular service from the cell phone provider and you're using your device as a hotspot. So it's connected to the internet on the one side, and it's providing Wi-Fi service to other devices that are connected to the internet. And while that is technically a multi-home device, that's a case where the network design is carefully specified so that you don't have a loop, and it's not a danger. So you can take two simultaneous network connections and bridge them. So there are cases where a network effect on one interface can spill over to another one, but then, believe it or not, there are people who are crazy enough to bridge two different network connections just to make things simple. They want to create a separate network or so on. And if you take two different connections and bridge them, that can cause huge issues. So what am I talking about here? If I go to my control panel and I look at network and sharing, and I look at my adapter settings, can everybody see my settings here?
Yeah.
Yeah.
So I have Wi-Fi connected. I have Ethernet that's unplugged, but I could, if they were active, I could bridge the connections. This is an option that you can access with a simple right click. And oh, there are handy YouTube videos on how to do this. And believe it or not, there are YouTubes out there where someone with an exotic foreign accent is showing you how easy it is to connect this and do that with your wireless bridge. And what they're doing is getting you to open the door under the guise of like some some well-known benefit. And what they're really asking you to do is to compromise your network security so that somebody can step in and get into your Kool-Aid. I'm telling you this for your own safety. And it's a Monday, and Mondays suck sometimes. But this is one thing I want to be very clear about. If you have more than one network connection, meaning your device is dual homed or triple homed, because there are such capabilities in some systems, gaming systems. Hello, gaming systems. Hello, we connect gaming systems to a hard cable because we want better networking when we're doing a network game. But then we forget that we're also connected to the Wi-Fi. Am I talking to anybody in the audience today? I'm just saying, it's one of those things we forget about. There can be cases where that dual home device poses a risk, whether the bridge is formed intentionally or not. There is malware that will form the bridge for you. That's what malware does. It exploits a condition, and then away you go. And then now they're looking at everybody's Kool-Aid that has nothing to do with the gaming console in your Wi-Fi home network, because that's broadcast. Hello, it's broadcast. Did I mention broadcast is like everybody sees your stuff? Hello, everybody? So they come in right out of the internet. Any questions about this? Does anyone have any thoughts or questions? Are there any interesting questions, given the information that was just shared, that would be appropriate to ask?
So when, I guess this has to do with virtual machines. So when we put a virtual machine in bridge mode, is that opening up the virtual machine for everyone else to see as well?
That's a great question. And the short answer is yes. When a virtual machine is, the network interface for the virtual machine is set to bridged mode. And here is what Milrain is asking. If I have a virtual machine here and I look at the settings and the network is set to as a bridged adapter, what's happening is that the virtual machine network interface is directly connected to the local network. And that is a similar concept, but it's by design. It's intended so that your virtual machine can talk and play in the same local area network. In that case, it's not posing a risk so long as the virtual machine creator understands that that virtual machine is present on the local network and can be seen on the local network by all the other systems. You can have the implementation of a Raspberry Pi that filters DNS and provides DNS in a home environment, and it's running on a virtual machine, and use a bridged adapter to do that. And that's actually a way of increasing the performance and the security of your network. We're going to take some time in module 6, our last module of the course. We are going to spend some time talking about special topics, you know, IPv6, the Internet of Things, and network security in particular. So when you look forward, You have special topics, and we're going to create and build a network application in Python. So thank you for asking that question. Are there any other questions? So when you connect two different types of network interfaces from the same device, a loop can occur, right? The loop gets larger and larger, and it can crash the entire network. There is a special protocol that's designed for larger networked environments like companies and agencies where this can happen and everybody's scratching their heads. True story, Albert Einstein campus, 2 or 3 years ago, an enterprising student in a dormitory was frustrated, plugged a Wi-Fi router into the Ethernet port in the room, set up a Wi-Fi network, fed out back through the Ethernet port in the room, and then there were dual connections. It was multi-homed. It created a loop. It was crashing the Albert Einstein network, as in the entire Albert Einstein network was having problems, performance issues, all kinds of issues. And they finally figured out what was going on, because when the loop got large enough to get into the segments of the network where the spanning tree protocol was there, they got some information and finally figured it out, but it took them 2 or 3 days. And they're much smarter and faster on that kind of stuff now. So it can happen, right? There are cases where a device is designed to take advantage of multiple connections, like Wi-Fi routers and smartphones, or virtual machines. But the important thing to understand is that you only want to bridge network interfaces for very specific purposes, and you want to carefully design what's going on there and how it's happening. Now, this would close out material in this module that is not covered in your textbook. So when you look at the textbook and you look at the slides, these first 5 student learning objectives are my gift to you from 25 years experience as a Microsoft systems engineer, a certified Microsoft systems engineer, okay? These are the kinds of things that we wanted to. Now, of course, there is some detail from the textbook where we wove it in, but in any case, if you're looking for direct connections between concepts for the first 5 student learning objectives, and hey, this isn't in the textbook, I'm calling that out right now, okay? There could be additional and related information in the cheat sheet from the University of Michigan. You should memorize this thing. Now we're going to go on to student learning objective F, right? So pioneers in the industry. It's important to understand some of the most important pioneers in networking, and Thomas Edison holds honors. What did Thomas Edison do? Well, all right, it says Nikola Tesla, right? We're inventors who pioneered electricity, right? And without their original work, we wouldn't have electrical or wireless networks. And that's important to mention, right? So the flow or pulse of current, where it's on, that represents a 1, and the lack of a pulse or current represents a 0. That's something to remember, is that when we use our internet today, we're standing on the shoulder of giants. And that's actually a quote, I think, that Newton said when people were giving him all sorts of accolades about the laws of motion, right? The 3 laws of physics. He said, "Oh, I'm standing on the shoulders of giants." He was referring to Galileo and some others. Alexander Graham Bell, has anyone ever heard of that name before?
The guy that created the first telephone?
Yes, and those were analog, old school circuit switched networks. We've gone over what that means in the first module. You connect a wire from the caller to the receiver, and that loop to and from the caller and receiver has to be connected all the way, right? So Alexander Graham Bell first invented the telegraph, but then turned it on its head sideways when he started working with audio. And without Alexander Graham Bell, if you've heard Ma Bell or the Bell Telephone Company, that's part of its origins there. Guglielmo Marconi is also a giant in the industry. Guglielmo, my apologies to Italians everywhere. Guglielmo Marconi invented the radio, right? So he studied and realized that you could carry the same audio over radio waves. And that was the first example of analog transmissions that allowed people to receive one-way transmissions. And that set the stage later for wireless data networks, okay? Two-way, right? So originally this was one way, where people are sending information by radio to another, and then they would stop transmitting, and then someone else would take turns transmitting back. And if you've ever wondered about the Titanic, there was a radio room on the Titanic. This was just a few years after Marconi invented the radio, and it was one-way communication where people would send SOS codes, or they would send the Morse code messages, or they would talk. And so people would hear them, but it wasn't always, not at first, wasn't always two-way. Robert Metcalf, or Bob Metcalf, was the one who started working in the aftermath of the first DARPA internet scenarios, and came up with the specifications for the first Ethernet interfaces, the first, the cable data networks that we know and use today. And he was working at the Palo Alto Research Center, which is pretty amazing because it was a Xerox facility, and what they wanted to do was to connect computer systems and terminals through a network so that people could print, they could print to the Xerox. And Palo Alto Research Center for Xerox is also the birthplace of what we call a GUI, a graphical user interface. Xerox machines had complicated menus, and in the same facility, not around the same time frame that Bob Metcalf was percolating Ethernet specifications, within a few short years, they were demonstrating icons that users could interact with on a touch panel for Xerox. Among the people who toured that research and development were two gentlemen by the name of Stephen Job and Stephen Wozniak. Anybody heard the name Stephen Jobs before? And Steve Wozniak?
It's not the Steve Jobs I'm thinking, though, right?
That's the guy that founded Apple out of his garage.
Yeah.
And he took that idea of the icons and used them in the first Mac. The Mac computer was the first computer in history to use icons. Well, sort of. There were actually Unix versions that used a graphical user interface called X11. It's kind of a long story, but they commercial use, right? Widespread use. So then later, Apple sued Microsoft because when Microsoft rolled out Windows, Apple claimed, well, you copied our idea for a GUI. Apple won the lawsuit. Then guess what Xerox did? Anyone?
I mean, did they sue as well?
They sued Apple and said, they said, no, you're the one that stole from us. You stole the idea of a GUI and used it in your Mac, your first Mac. And that was introduced during a Super Bowl commercial, right? So there's actually a classic Super Bowl commercial where the first Macintosh computer is going to shatter everything. And they made a huge fortune, right? And Xerox is like, yeah, not so fast. So you sued Microsoft, but everybody needs to know the real story. We're the ones that developed it, right? And Bob Metcalf, the one that did, Now, Palo Alto is right in the heart of Silicon Valley in California, okay? Fascinating history, the history of Silicon Valley. There are a number of books. If you're interested in reading about it, I can provide you with a reference list, but you can also Google that. There's some really cool history there. And most people don't realize the role that Xerox has played in the formation of the things we use every day, right? So just got to give credit where credit's due. Charles Hard Townes and Arthur Leonard Shawlow invented the laser while at Bell Laboratories. And then there were other pioneers who extended that research, and Charles K. Cow completed the initial work on a suitable media fiber made out of glass. So glass fiber, fiber optics is glass. It is the same glass that shatters when you drop it on the floor, except it's pulled into a very thin strand. And that glass is like really clean, it's like a really clean spout of water where the laser can ricochet down inside the internal surface of that strand. And nowadays, fibers can be a fraction of the width of a human hair. So Charles Cow, fiber optics, okay? Townes and Shawlow, lasers. Fourier. So you can't really talk about pioneers who changed the world without giving proper homage, without extending a proper homage to the French. There was a team of individuals, and I think we mentioned this, we actually mentioned this in one of the later modules, that developed the foundation of networking based on TCP. And we use TCP IP everywhere on the internet. When we get to layer 4, we'll talk about that. But before that point, Jean-Baptiste Joseph Fourier developed the mathematical method called the Fourier transform that later led to the innovative embedding of waves within waves. What are we saying? If you have radio waves, you can embed data on top of that wave by putting a wave on top of a wave. It's called modulation. And this is a concept that we'll refer to in greater depth at a later time. But Fourier determined that there was a mathematical relationship between the carrier waves and the embedded waves, that if you have higher frequencies, you can carry more data. There's actually a mathematical equation. Simply put, if the frequency is multiplied by the bits per sample, one can calculate the data capacity for a given transmission method or media. And it's a simple calculation. If we have 8,000 samples per second in terms of waves, when we say samples, that's a broader term to mean waves, pulses, whole variety of things, right? Times 8 bits per sample, right? If you modulate, if there's modulation, then you have 64,000. How do you get that? 8 bits times 8,000 per second is 64,000. We call those samples in bits, thousands of bits per second, or kilobaud. The word baud means BPS, bits per second. So baud is another term you're going to hear quite a bit. K is the metric prefix that means 1,000. So 64,000 baud, right? Any questions? So when you reference student notes, and by that we mean, go ahead.
Yeah, I was just, okay, so what you just said about, I guess, compounding the waves, right? The composite waves together in order to carry information. Is that how they discovered, I guess, packet switching? By putting that data on top of that wave and then sending it out? And then And then like I guess going through the IP and then going back up, is that like what do you mean by like decomposing it? Like unwrapping the package that we learned last section, like the PDU and the SDU?
Yes, the short answer is yes. I do want to call out that Fourier was the one that developed the mathematical relationship between carrier waves and embedded waves, but it was Harry Nyquist. Harry Nyquist basically extended that original work by Fourier and came up with a simple calculation that it's a ratio of the frequency of a wave where you can calculate the baud rate capacity or the data capacity. But yeah, the short answer for your question is yes. It is these developments that paved the road that allowed for digital and packet switch networks to be birthed. So as soon as people figured out, okay, we can actually use the signal modulate the embedded waves, the signals that are embedded in the carrier waves, we can represent ones and zeros with the embedded waves. And so that's where the waves can represent ones and zeros. And there is a precise, there's some really fascinating graphs about how they do that depending on the wave algorithm. Signal science is always evolving, but it's pretty complex stuff. And the important point is to remember that without this original work, nothing would have been possible. So we ask you to reference student notes and the University of Michigan. When I say UMIC, I mean University of Michigan cheat sheet. Student notes in here happen to be the slides. So selected slides by the author that in the previous module, those were called student notes. And when you open this up, you'll see slides from the different chapters that are listed here. So there is something that's omitted, namely the physical legacy of media punch cards and portable disks that were used originally to transmit data. And so this is a part of, and Comer makes, I think Comer makes mention of this, but only briefly. In the history of computing science, there was a stage of technology use that involved a network called SneakerNet. And every now and then you'll hear people talking about sneakers and the use of, so you have punch cards. So computers used punch cards instead of magnetic media. Instead of using disks, floppy disks, or hard disks, or USB disks, they used cardboard cards that were punched. There were holes that were punched to represent the ones and zeros. And so people would carry the data embedded on the punch cards or embedded on the portable disks. And that's how they transmitted the data. They would literally get on a plane and go to another computing center and then load the stuff up. And that was the first original technology network. It was called SneakerNet, okay? Hand-carried media. But that same term is also used in modern day to talk about any other hand-carried media. So SneakerNet would be, okay, I can't transmit this, it's too big. Let's put it on a thumb drive and I'll carry it to the next screen on a thumb drive. That's Sneaker Network, in case you hadn't heard that before. I did want to take a quick moment to glance at the cheat sheet that we're referring to all the time for the University of Michigan. And so this is the industry standard model for networking, the internet protocol stack, right? And here it talks about bits on the wire, right? The physical layer. And this is where you see some really helpful references. Glass fiber, they're talking about fiber optics. Twisted pair is a reference to Ethernet cable. Coax is another method of transmitting ones and zeros that cable companies use. So coax cable is still copper, but there's only a single lead, where Ethernet takes 8 leads to send and receive data, it's still serial data being sent and received simultaneously. Here, it's radio frequencies with modulation that allow for multiple levels of bits to flow to and from, right? You'll see this term called topology. Topology is a fancy word that means network wiring plan. So when you hear the word topology, we're talking about how the wires are arranged and how they are connected. If they're connected in series, like a set of lights on Christmas tree lights, that's called a bus connection. There's a ring topology or ring method where you form a ring of media and each device is connected to the ring and they pass a token around. So there's often a reference to token ring, or it's a fiber optic ring where the data is, everybody takes turns transmitting. And then one of the most common topologies is the star topology, where you have a hub or a switch or a router, and there are many different devices that are connected, and it forms like a star. So that's where you get the term star topology. In recent days, the idea of a mesh network where it's every device is connected to every other device. Mesh networks are not as new, but it is another type of topology. There are a number of other diagrams. So this is an example of the modulation and how the signals are like overlaid on top of carrier waves. And so you can see how the voltage fluctuations result in the signaling that is interpreted as ones and zeros. So that's really cool stuff. I'm not going to go into all the detail here. I am going to pause for about a 60-second break. Let's just stand up and shake out stuff, and we'll go back to our study guide and get a little further today.
Carol?
So when we say taxonomy, and this is part of our, this is Student Learning Objective 6, a media taxonomy, including speed and distance, Ethernet, fiber, and Wi-Fi, right? This is a diagram that's in the student notes or instructor provided slides. And what we do is a taxonomy is often referred to as a hierarchy. That's a $64,000 word that means we have a main category, then we have subcategories, and then we have sub-subcategories. Whenever you have a breakout in academic resources, research and all that kind of stuff, and they talk about a taxonomy, or they use the related word hierarchy, which is spelled H-E-I-R-A-R-C-H-Y. It's a fancy word. It means you have a system of categories that starts with main categories, subcategories, sub-subcategories, even sub-sub-subcategories. One common science example of this happens to do with the way we name animals and plants, living organisms, right? So there's actually a naming mechanism: kingdom, phylum, subphylum, class, order, family, genus, species. You have subtypes and so on. Then you get down to the actual formal name for a living thing, and it's based on, well, anyway, that's biology. Any questions about what this diagram means in terms of what this is? That's the main category, energy types. Then we have subcategories: electrical, light, and radio. Yeah, everybody see this?
Yeah.
And then we break those down even further. We have twisted pair and coax and electrical. We just showed you pictures of both. Ethernet and cable company connections. Oftentimes connections are referred to as handoffs. So when we're talking about the point of connection for a local network, that's called a handoff in industry. When you talk about light, you have optical fiber. So there's that glass fiber, right? A strand of glass fiber that's just a fraction of the width of a human hair. You have infrared light, which if anybody has like a universal remote, that's what infrared is and how it's working. It's controlling data changes and inputs based on the pulses of invisible red light. Infrared is also the heat lamp that keeps food warm at a restaurant, coincidentally. Laser. So you have laser light, that's coherent light where the waves are all aligned. And then of course, electromagnetic, you have terrestrial radio and Wi-Fi. So Wi-Fi fits into this category right here. Terrestrial radio includes Wi-Fi. It includes 5G. It includes Bluetooth. It includes near field communication. It includes WiMAX and Zigbee and all sorts of other cool radio-based technologies that you may or may not have heard about. And then there's also satellite, right? So Elon Musk has a new Starlink, and they've had satellite internet for quite a while, but the latency has been very bad. Latency means the delays between pulses, right? Because of the distance. Elon Musk is kind of shattering that with his new network for Starlink. I'm going to try it in March when my broadband VI contract runs out. But there are trade-offs with satellite, and Elon Musk can, well, he's a bit of a maverick at times, and if he decides to make changes, he just makes changes. So, you know, we're going to see what happens. He's another pioneer to look at because of what he does with solar energy and with his cars and so many other technologies, right? Any questions about satellite and all that?
So in regards to this taxonomy, it's not like electrical is higher than light and light is higher than electromagnetic. They're on the same level, right?
That's correct. That's
Okay.
just how the author chose to organize the chart. It's not like electrical is any better than light is any better than satellite and all that kind of stuff. So you could, you know, flatten this on the top of a table and they could all be on the same level, so to speak. It's not like electrical is better than light and light is better than radio. So that's a good observation. Like, you know, everybody should be using this if they can and using that if they have extra money. But you know, this is the way the common man connects. That there's no interpretation that we would want you to conclude based on the way the chart is organized. They could have done it in alphabetical order, you know, where they had like electrical and then electromagnetic, or vice versa, and then light. So there is a really cool, and this is sort of irritating, but cool. So there are lasers that work across air, and it's like wireless. So there's a pulse of laser between a collector and a sender. It's called optical wireless communications, or free space optical. So it still uses laser and light, but it's the strength of the laser beam that has to get to the other side. And if there's a lot of heavy weather, like a torrential downpour with a tropical storm or hurricane, or there's magnetic interference in the atmosphere from solar flares, basically laser can be disrupted or deflected with poor conditions in the atmosphere, smoke or smog, you know, precipitation and so on, right? Heavy snowstorms can be really bad. In many regards, it kind of parallels the way that wireless works. So they call it optical wireless. And that's something that I want to make sure is still, yeah, that still holds true. So it's short range through the air, transmissions of labor. There's no physical fiber. So it is fiber optic without the fiber. There are two lasers on either end, and it's across open air. And again, there's a different terminology for that technology, right? And then free space optical. So free space optical, here's how the transmitter works, right? You can get a gigabit of data, and you can span a distance of 4 miles or 2.5 miles. Well, it's gotten better. So it's more like 4 miles now. And you don't have to have fiber optics. You don't have to have copper. So you can set up a tripod in the aftermath of an earthquake or hurricane. These things could quickly allow for the rebuild of a backbone or emergency data networks for recovery efforts. And this is something that's really significant. We should take, see, and here's a kind of a mock-up of how you could use part of this fiber optic in the air, right? Free space optical to transmit data. And yes, if somebody gets in between or this is blocked, you know, it's line of sight. So 11 miles, the curvature of the earth causes a problem. So you have to raise the antenna significantly if the transmission distance exceeds 11 miles. But in general, it's like 4 to 5 miles max because of the atmospheric conditions. So I just wanted you to be aware that there's a really cool option out there. And I think that this is worth a closer look for territories like ours, where we have serious challenges. Let me check here. Yeah, all right. 1 second, please. I'm gonna update this. Any questions about free space optical or optical wireless communications, right?
I saw like an example of how optical wireless communication could be used, and it was on the Wikipedia that you had just put up. It was like for space shuttles.
Oh yeah, yeah. The use of optical wireless in space is really sensible, because in space it's a vacuum, there's no atmosphere, so your distances can be a lot further. And I'm pretty sure that's how the satellites in Elon Musk's the backbone of his Starlink are working. They're using optical or free space optical between the satellites, right? I want to talk about copper just a minute before we close out. If you have a pair of wires and they're straight, and you're pulsing ones and zeros and ones and zeros, send and receive. Does everybody see this?
Yeah.
Yeah.
Okay. And let's say you have a source of radiation in the room, like a magnetic field from a strong magnet, or the magnetic field of the earth, or flare up from the sun, any kind of, or here's a common one, fluorescent lights. Fluorescent lights create huge magnetic fields. And if you have this data wire that's near a fluorescent light, what happens is that there's interference that's much higher on one line compared to another. And this mucks with the send and receive. Whichever side, sending or receiving, is closest to the fluorescent light, you lose those data signals a lot faster. So Bob Metcalfe and the Ethernet folks came up with this idea of twisting the wires, right? And when you twist the wires, what happens is that the influence of differential radiation effects is balanced out. Let's say that again. The difference that you see here between radiation effects that occur because of the distance between the one copper wire and the other copper wire relative to a source of interference like a fluorescent light. When you twist the wires, because the wires are twisted, the interference between the wires is balanced out. See how it's 5-3 and now it's 5-3 and now it's 5-3, but in this case, the gray wire is 5 and now the gray wire is 3 and now the gray wire is 5 and the gray wire is 3. You basically get much greater distance when you twist the wire. You've heard the term category or Cat5. That means there are so many twists per distance. Cat6 is higher twists. The higher number of category Ethernet wire, the higher the number, the greater the number of twists, and the greater the distance you can, or higher the data you can transfer across that wire, because the influence of nearby radiation sources doesn't wash out the ones and zeros. Okay, so that's a mouthful, but what I want you to understand is the higher the category of wire, the greater the number of twists per inch or per centimeter. And that means the higher the data that can be carried, or the greater the distance can be carried, or both. Right now, category 6 is kind of a recommended standard. If you want gigabit or higher wire speeds, 10 gig wire speeds, you have to be running Cat6 to do 10 gigabits per second. We're talking bits per second, not bytes per second, okay? Now, we're gonna talk about the differences between solid core wire and stranded core wire on Wednesday. We'll stop here. Any questions, given the information we have just shared about Ethernet cable or about any of that, optical, wireless, etc.? Given the information provided, can anyone think of some interesting questions to ask? Going once.
Yes, it's more of an observation. So does the free optical, like you were demonstrating, like you showed in the picture on Wikipedia, you said that because of the curvature of the Earth, it might get, like the signal might get disrupted, right?
Right, which is oftentimes why they use satellites to ricochet. That's how you get over the curvature of the Earth. Yes.
Oh,
Or they
so
put the transmitter on a mountaintop.
mm-hmm.
And when they put it on top of a mountain, they can go that much further across the curve.
Okay. So I guess my observation, it's a silly one, but my observation is that's just another way to disprove flat earthism, or flat earthers, I guess. Because doesn't that mean like the
absolutely.
Earth is...
Yeah, absolutely.
Okay.
Yeah, if you had a tripod at ground level, and it wouldn't make it to St. Thomas. But if you put it on Eagle Mountain and shot to a mountaintop on St. Thomas, it would make it. And that's proof that flat Earth is ridiculous. Yeah. And I'm sure they have an explanation for how that is and why it is. Right. Like,
Yeah.
oh, the light beam sags because of the gravity, or no. Light beams don't sag. Yeah.
No, there's one guy, he said that there's the God's energy or God's waves or something. It was bizarre stuff.
Yeah, bizarre.
Yeah.
Well, this concludes our session for the day. Thank you for joining us. We look forward to seeing you on Wednesday, and goodbye for now.